Galileo said that the book of nature is written in the language of mathematics and geometry. And so let's talk a bit about geometry. What does geometry mean, and what does it mean? What did it mean for Galileo, and does it mean for now in physics? Well, you probably all heard about Euclidean geometry, which talks about points, lines, circles, and the relationship between them. For example, that given 2 points, there is a line that goes between them, and so on. And we use this geometry to describe images and in computer graphics and so on. Okay, I think did I press something wrong? Are you still seeing the? Are you still seeing the screen? Or um, okay, I lost my screen. Okay, are you still seeing the screen? Are you still hearing me?
Yes, yes.
Okay, sorry. Okay, so we use it to describe images, and geometry arose from the technological necessities of the time. For example, measuring fields, charging taxes, etc. And the Greeks formalized and abstracted the rules of geometry, and they set a set of axioms. So there are about 5 axioms, which are the basic principles from which you can derive all the properties of geometry. And for example, one of the axioms says that given 2 distinct points, there is a unique line passing through them. And the other ones are similarly simple, so simple, more or less obvious things. And this process of defining geometries has continued to this day. And we can now imagine curved geometries, higher dimensional geometries, and so on. And geometry is a very basic notion that we can find it in some unexpected places. So we can even find it in some children's games. So let's see how this example works. So there is this children's games that perhaps you know, perhaps you don't, but the idea is that you play some cards, and then you, given 2 different cards, you have to find the image that they have in common. So for example, these 2 cards have this image in common. And similarly, these 2 cards, for example, have this image in common. And you have to find the image before the other person. So that's what the game is about. Now, where is the geometry here? So notice that given 2 different cards, there is a unique image in common. And this should remind you of the fact that given 2 different points, there is a unique line in common. So these properties of images and cards has the same have the same property as the property, this axiom in geometry, that given 2 points, there is a unique line in common. Now, um, the other axioms of Euclidean geometry are not satisfied, but there are other axioms which form the so-called finite geometry, which was developed in the 17th and 18th century. And this set of points and cards obeys those axioms of the finite geometries. So this is a simple example how we can find some kind of hidden geometry in some everyday thing. Now, also there is a higher dimensional geometry behind these language models, such as ChatGPT, where words are represented as points in a higher dimensional space. So usually they choose space of, let's say, 12,000 dimensions. Now, the Eratosthenes showed that the geometry of the Earth is curved by doing this famous experiment where he was comparing the shadow of a vertical stick that was at the equator versus one that was further from the equator. And by determining the length of this shadow, he could determine this angle. And by measuring this distance, he could determine the surface of the Earth. And one conclusion of that is that the surface of the Earth is not flat, but it's a sphere. So it doesn't obey the principles of Euclidean geometry, but it's really curved. So in fact, Euclidean geometry is actually wrong for measuring fields because the surface of the fields are in the surface of the Earth. But it's only wrong if you consider a field which is very big. So like a very big triangle on the surface of the Earth will have angles whose sums are bigger than 180 degrees, while a small triangle will have the angles will sum to almost 180 degrees. So we see an example where if the field is small, we obey the principles of Euclidean geometry. If it is very big on the surface of the Earth, we don't. We have to take into account that the surface is curved. So this is an example of going between the flat geometry and a curved geometry. So now let's go back to physics. We'll talk about some other things first, and then we'll go back to geometry. And we'll recall an important principle, which is the principle of special relativity, which says that if you have two observers moving with constant velocity relative to one another, they both observe the same laws of physics. And this first principle was already known to Galileo. It goes back to Galileo. So the new aspect of special relativity is that the speed of light is the maximal speed of propagation of signals. And this is viewed as a principle of physics, and so it should be the same for both observers. So that's the new aspect. So this in particular says that if you have an observer at rest in his laboratory and an observer that is moving, and we have a beam of light, such this moving thing denotes a beam of light, the two should measure the same speed. I mean, intuitively, you might think that this moving observer would see a lower speed. But what happens in nature is that they both actually see the same speed. And what this implies is that what this leads to is that it's convenient to join space and time into a new kind of geometry, which we call spacetime. This in some ways is similar to what we did with the story about the card game, that we are seeing a geometry in this new structure of space and time. And so here, the idea is that the points are going to be, the points of the geometry are going to be the events. So things that happen at some time, at some place. And the lines are going to be the trajectories of particles. And straight lines would be trajectories of particles that move at constant velocity. So for example, we sometimes draw diagrams where we represent one of the directions of space along the horizontal direction, and then one of the time direction along the vertical direction. So this vertical line would be a particle at rest. It's not always, it's always at the same position in space, but time is moving, is going forwards as we move up. And these are two events along that happen on this particle. Could be when the clock says a particular time, let's say the beginning of this talk, and then this present time of the talk. And then similarly, we can have two moving particles. So there's a particle moving to the right, and it crosses the particle at rest at this instant. And we can have particles that move faster. And we have a fastest moving particle, or the fastest moving object, which would be a beam of light. It could cross, let's say a beam of light that crosses at this point will have this trajectory. And that's the maximal speed. So there cannot be any line that moves faster than this line. So that we could not draw a line that, let's say, goes along here. So the conclusion is that out of space and time, we can make a new type of geometry. Now, we'll now make a small apparent detour from geometry. We'll just remind you of the force of gravity. So there is the famous Newtonian gravity, which we learned in high school. And that basically consider a situation where you have a very big mass and a small mass separated by some distance. Then the Newtonian gravity says that the acceleration that this mass feels is proportional to the Newton constant, the mass of this particle, and the distance between the two. Well, the distance square, 1 over the distance square. Now, this has two features. One is that the acceleration of this light particle m is independent of its mass. So the mass m does not appear in this formula. The other property that this has is that it is an instantaneous force. So the direction of the force points to where this big mass is at the given instant. So if we suddenly move this particle, then the force will have to change direction instantaneously. And this is not good for special relativity, because in special relativity, the signals should propagate at the speed of light. So if you move this, okay, okay, good. So so that's not good for special relativity. So if we move this particle at time equal to 0, so it should take some time for this particle to notice that this particle has moved. Okay. So Newtonian gravity does not obey the principle of special relativity. Now Einstein had an idea which he called his happy thought, which is that if you fall freely in a gravitational field, your weight disappears. So let's imagine the following experiment. So imagine that you are standing in an elevator and you are, let's say, standing on a scale that is measuring your weight. So the scale measures your weight if the elevator is not moving. Now, if someone cuts the wires of the elevator and the elevator starts falling down, then you will be falling down, the scale will fall down, and so on. And you will be basically floating, and the weight on the scale will just say that the weight is 0. It looks as if your weight has disappeared. So the conclusion of this is that you are falling freely in a gravitational field. The main effect of gravity, which is your weight, disappears. Okay, so that's a peculiar feature of gravity that is related to this first property of gravity. And this is what happens with astronauts and so on. Now, this principle led Einstein to formulate the theory of general relativity, which is Einstein's theory of gravity. And the idea is that the geometry of spacetime is not flat, but is curved, and that the particle moves in this spacetime along the shortest trajectory. So, and that matter curves spacetime. So the fact that all particles move in the same way in a gravitational field is related to the fact that all particles are seeing the same geometry. And then there are some Einstein's equations which say that the curvature of that spacetime is proportional to the frequency. Now, spacetime is a curved geometry. So the idea is that points are events. Okay. So the idea is that points are events. Straight lines are trajectories of observers that are falling freely. And for our everyday experience, we are pretty close to flat space. Now we can see that space-time is curved by doing an experiment similar to the experiment that Eratosthenes did, that the Greeks did for determining the curvature of the Earth. So there is this famous example of seeing gravitational lenses where you have a faraway galaxy and then some other galaxies more nearby that are curving the geometry, and so you see multiple images of the faraway galaxies. So the light rays are bent as if you had a lens, and you see a picture roughly like this. Now, one interesting prediction of this theory is the fact that there are gravity waves, and these gravity waves were first detected in 2016, so relatively recently. And then there are two very surprising predictions, which are black holes and the expansion of the universe. And I'll explain these two surprising predictions in a second. Now, these predictions were so surprising that Einstein himself didn't believe these predictions. So, for example, there's this famous phrase that Einstein told Lemaitre. Lemaitre was the first to discuss the expansion of the universe. Well, one of the first, I guess. Friedman also did it before, but Einstein told him, "Your math is great, but your physics is dismal." So we now have great observational evidence for both. So there is this famous image from the area around the black hole at the center of the Milky Way, at the center of our galaxy. So the black hole would be around here, and this is the gas moving around the black hole. And then we have evidence for the expansion of the universe that you probably all heard about. We now will turn to a new topic, which is the idea that we have quantum mechanics. So there were two revolutions in the early 20th century um, that took us away from classical physics. So one was special relativity and then general relativity. Um, and then the other one has to do with quantum mechanics. So quantum mechanics is a new type of description of physical systems, which is intrinsically probabilistic. So we can only calculate probabilities that the system does one thing or another. And there are things like the uncertainty principle that tells us that there are some things that you cannot know at the same time. For example, the position and the momentum of a particle cannot be known at the same time. And quantum mechanics explains chemistry, explains atoms, matter, etc. It is a strange explanation where atoms are mostly empty space, um, and it requires a lot of work to explain relatively simple and obvious things. So, for example, the physical appearance of most substances are emergent properties, which arise from a large number of quantum particles and their interactions. Um, so, for example, for us, a mountain feels very solid. Similarly, for an insect, the water seems solid, but if we were to stand on water, we would sink. Okay. However, in both cases, they consist mostly of empty space, the space between the electrons and the nuclei of the atoms. And if you have a neutrino or a dark matter particle, they can go through the whole Earth without interacting with any of our particles. So they feel as those particles do really feel as if it was empty space. So now we'll discuss yet another concept. In between the 30s and the 70s, there was a new theory developed, which was the joining quantum mechanics and special relativity. This is sometimes called quantum field theory or particle physics. So it comes from making quantum mechanics obey the principles of special relativity. So how does that work? Well, it describes the interactions between elementary particles, and for each so the idea is that there are elementary particles such as an electron, and the interactions are described by the creation of a photon. So an electron emits a photon, and this photon interacts with another electron, and that way we describe the electric force between two electrons. Now, in the same way that there was some geometry that we use to describe pictures, we draw this type of pictures which are describing the trajectories in space-time of electrons and photons and so on. And behind these pictures, there are some formulas which let us calculate the probability that this whole process occurs. And by calculating that, we can make predictions that we test in particle colliders that we can check explicitly. So in this way, we describe, basically with this kind of theories, we can describe all the matter that we directly see. So all the matter that makes us, the matter that makes faraway stars, and so on. Now, an important question that remains is how to incorporate the principles of quantum mechanics and general relativity. Now that's something that we don't yet completely know, a completely accepted theory to describe this. So this hypothetical theory is called quantum gravity. So the quantum mechanics of gravity, or the quantum mechanics of space-time. Now there are two approaches for understanding this problem. So there is one which is an approximate approach, which is similar to the approach in quantum field theory. I'll describe it briefly. And there is a more precise approach that would be the full theory of quantum gravity. So I'll describe these two approaches. So what is the approximate approach? So the approximate approach would be to describe the force of gravity by saying that we have particles, and the force of gravity is due to the emission of a new particle that we call the graviton. So this is the fundamental quantum of gravitational interactions. Um, and, and this approach works well when the radius of curvature of the universe, or the region of space-time that one is considering, is much larger than the Planck distance. Now, what is the Planck distance? So the Planck distance is a combination of some fundamental constants of nature, the Newton constant, the Planck constant, and the speed of light. So this Planck constant is related to the quantum effects. And it's a combination that is a distance, which is a very tiny distance, 10 to the minus 35 meters. This is very, very, very small distance. And this is supposed to be the distance at which the quantum gravity effects become large. Okay? At longer distances, the quantum gravity effects are going to be small. Now, this is a theoretically computed distance. No one has measured such a small distance. In fact, the smallest size that we can explore today with the best particle accelerators, the Large Hadron Collider at CERN, it's a distance of order 10 to the minus 18 meters. So much, much larger than 10 to the minus 35 meters. Okay. So that means that this simple approximation is enough for most of circumstances of daily life, and in fact, almost all places in our universe. Now, there are some cases where this approximate approach does not work, and this happens at the singularity at the beginning of the Big Bang, at the very beginning of the Big Bang, or the expansion of the universe before inflation and so on. And also, there are similar singularities in the interior of a black hole. Now, notice I did not explain the word singularity. So singularity just means that there the equations of general relativity and quantum mechanics break down as we know them. And we don't know what is happening there. So even we don't know what happens at the singularity. So it's a place where a mysterious location. Now, to understand what happens there, we need a full theory of quantum gravity, so a more complete theory. Now, we'll discuss the full theory later, but before talking about the full theory, we'll discuss some important successes of the approximate approach. Now, we'll see that it gives rise to a big surprise for black holes. So the laws of quantum mechanics imply that black holes emit thermal radiation. This is a discovery made by Hawking in the 1970s. And Hawking's formula says that the temperature of the black holes increases as the size of the black hole decreases. So if you have a black hole, a relatively large black hole, it's very cold. And then as you make it smaller, it becomes hotter. And you could have a black hole which is so hot that that it will look white. So let's just see what the size of that black hole would be. So let's first consider a black hole with the mass of the sun. This type of mass is the type of masses that are produced by astrophysical processes, so a few times the mass of the sun. And for those black holes, for astrophysical black holes, this temperature is very, very, very small. So all these zeros above the absolute zero of temperature, 0 Kelvin. And so for these black holes, this temperature cannot be seen. So the Hawking effect has not been seen for astrophysical black holes. Now you could imagine a black hole which is very small, which is the size of a bacterium. This is roughly the size of that corresponds to the wavelength of visible light. And such a black hole would have a temperature that is comparable to the temperature at the surface of the sun, and you would see it white. So such a black hole would be seen as a very tiny white dot. And for this reason, I say that this is a big surprise, because it shows that you can have the paradoxical situation that you could have a white black hole, so a black hole that will look white to your eyes. So somehow the name of a black hole was not chosen properly for such small black holes. Now, one question is why we have this effect. So I explained the result, but I didn't explain why this happens. And I'll now give a kind of long explanation for why it happens. And the purpose of this long explanation is to prepare some concepts that we'll discuss later. Um, the, the important thing is that in quantum field theory, so in quantum mechanics and special relativity, the quantum vacuum is a complicated object. And in particular, if you look at the small region of the vacuum, you will, and you go and you measure, for example, the electromagnetic field, each time you measure, you will see a different result. And that's a bit related to the uncertainty principle, that we cannot have an electric and magnetic fields which are exactly zero. And so this little video represents that fact that each time we measure, we'll get a different answer. And not on, yeah. On the other hand, the whole vacuum is simpler. So if you measure two separate regions of the vacuum, you maybe see different random results here on the left, but you see some other random results here on the right. But these two random results are correlated in the sense that if you see the electric field that is positive here, it might have to be negative here in such a way that the average over a very big region would have to be zero. Now let's try to describe this with an analogy. So let's say someone gives you a portion of a sentence. For example, Mary stepped out of her. So this is a portion of a sentence. And you can ask, what does this sentence mean? Well, it doesn't have a clear meaning because we know that the sentence is not complete. We know it involves Mary, but we don't know the full meaning. It could end in many different ways. But if someone were to tell you the full sentence, for example, Mary stepped out of her comfort zone by explaining quantum physics to a group of investors, then that is a more complete sentence. You get a well-formed sentence and has a clear meaning. Now, if you only have a portion of the sentence, we lack some information. Okay. We can quantify the information that we lack by listing the various ways to complete the sentence. And in some sense, there is some ignorance quantified by some idea that is called entropy, which is an idea in information theory, which has something to do with the number of ways in which we can complete the sentence. Now, the analogy is that the full vacuum is like a well-formed sentence that has a clear meaning, and a small region of the vacuum would be like part of the sentence that does not have a clear meaning. So now let's just return briefly to black holes. And so now we'll talk about the space-time geometry of a black hole. So we'll discuss in a bit more detail what the geometry of the black hole is. And so here we are drawing a picture of a representation of the black hole geometry. Now we are discussing here, let's say, a spherically symmetric black hole, and we are not drawing the angular directions. We are only drawing the time direction and the space direction roughly horizontally. So by the space direction, I mean the radial direction that moves you away from the black hole. So as in previous space-time diagrams, time basically goes in the vertical direction, and the radial direction away from the black hole is this one. Now, in a black hole, there is the region far away from the black hole is this region that is here, very far away from the black hole. And we call this the outside of the black hole. Now, in the black hole geometry, there is a region that contains, I mentioned the singularity, so this is a region where the effects of space-time curvature become very large. Around this region, the geometry looks like basically a collapsing universe, something where the curvature is becoming larger and the directions of the sphere are becoming very small. And if you were to find yourself in this region, you would die due to the gravitational forces. Now, if you, let's say you are in some point here, in what we call the outside region, then you could move in. If you move to the left, so if you move inwards, you might end here at the singularity. So that would describe you falling into the black hole. On the other hand, you could have a big powerful rocket, and then if you start here, you can start moving out, and then you can go very far away from the black hole, and you can avoid falling falling inside in the region that is very singular. Now, if you find yourself, let's say for some reason in this point here, then you could fall into the singularity, but the interesting thing is that you cannot escape, because if you were try to escape, you would have to move at the speed of light, and the speed of light is, let's say, at the line of 45 degrees in this diagram, and then you would try to go out, and then you would fall into the singularity. No matter how powerful your rocket is, you will fall into the singularity. So there is a dividing line between falling into the black hole and not falling into the black hole, which we call the horizon of the black hole. So this is just an imaginary line, imaginary in the sense that you don't feel anything special when you are falling. If you are moving here in this space-time, you don't feel anything special at the horizon, but this horizon sort of puts an imaginary boundary between the regions from which you cannot escape from the regions from which in principle you can escape. Okay. So that's the geometry of a black hole. So now let's imagine we have the vacuum of the full quantum field theory, so the full quantum vacuum, quantum relativistic vacuum in this full space-time. So space-time consists of both regions. And however, if you are an observer that sits purely outside, you cannot receive any signal from the parts of the vacuum that are in the inside region, okay? Because nothing can move faster than the speed of light, so no signal can go from this region. So if you are outside, you only see part of the vacuum. So you only see a portion of the full vacuum. And it is similar to in the analogy that we said before. So the full vacuum would be a full sentence, and we are only seeing part of the sentence because we are outside the horizon. That means we would see only part of that full sentence. And therefore, this leads to some randomness, some ignorance, and the type of ignorance and randomness is such that we can assign a temperature to it. So always when we have some object at finite temperature, we also have a somewhat similar randomness, and this is essentially the physical process that the physical reason why we have a temperature. Now, for a black hole, we can calculate the entropy or the amount of disorder by using the laws of thermodynamics. So if you know what the temperature of some object is and what its energy is or its mass, we can calculate the entropy. And you find a surprisingly simple formula for the entropy, which is that the entropy is equal to the area of the black hole horizon. So the horizon is a spherically symmetric, well, for a spherically symmetric black hole has a certain area, two-dimensional sphere with some area. And if you measure that area in Planck units, so this is a very tiny distance. And so for a macroscopic black hole, this is a very, very big entropy, much bigger than the entropy of any object of a similar size. But well, this is the entropy that we would assign to a black hole. And then the second law of thermodynamics, which says that the entropy should increase, is related to classically, at least in classical general relativity, the area always increases. So if you have processes like black hole collisions and so on, Hawking proved that the area of the black hole always increases. So we have an interesting connection between geometry and thermodynamics in the context of black holes. And this is something that was understood in the 70s. Now, black holes emit radiation, they lose mass, and they evaporate. And this is irrelevant for astrophysical black holes. As I mentioned, the temperature is very small. However, imagine you had a small black hole, so the laws of general relativity in principle allow for a small black hole of a mass of 1 kilogram. And then, so this is an object that in principle could exist. It's not known that to be produced but we can wonder how it would behave. And if if it was in classical general relativity, this is just a black hole that would exist for a long time. It doesn't do much. However, if due to this effect of Hawking radiation, it will emit a lot of Hawking radiation, and it will convert all that mass into energy very, very quickly, and it would be worse than a nuclear bomb. So very different behavior between a classical black hole and a black hole which where we include Hawking radiation. Unfortunately, there are not such black holes around. And okay, so we described some results for black holes from the approximate method. But there are some questions about black holes that we could not answer using the approximate method. And these questions are, for example, what precisely comes out of a black hole? How do we recover the information of the matter that formed the black hole? And this is a question that we don't care so much from the practical purposes, but we care about it from the conceptual point of view, because we like to understand whether the process of black hole formation and evaporation is consistent with quantum mechanics. So for that, we will need the full theory. And we have a theory under construction, which is the so-called string theory. Now, it's not a full theory, so there are some aspects we don't understand, but there are many aspects we understand. It's a bit like seeing the outline of a building like this. So we think there is a theory behind, and we're making steps to understand it. Now, of course, without mathematics, which is what I will try to give in this talk, it will be less clear, but hopefully you'll get the idea. Now, we are learning interesting things about the quantum aspects of black holes, and I will focus on just one aspect of this theory, and this is the idea that spacetime could be an emergent concept. Spacetime itself could be an emergent concept. So the idea is that, so in this picture of the insect going through the surface of the water, we have a geometry, which is the geometry of the surface of the water. And that's a geometry that emerges out of the interaction between water atoms. So the atoms of water, the molecules of water, sorry, are, they condense and they form water, and they're separated from the gas, from the vapor. And in the presence of gravity, it will form this well-defined surface. Now, the idea is that maybe the geometry of space-time is somewhat similar. And so the question is, what are somehow these atoms of space-time? So what is the more fundamental description of space-time? So in the case of water, we know that we have the atoms of oxygen and hydrogen and so on, and they describe the water. Are there some similar space-time atoms? So the idea is that yes, but the elementary atoms or qubits are in some sense live far away. So this is the idea of holography. So this is the idea that we can describe the physics of gravitational spacetimes in terms of particles or qubits that live very far away. So this is, and the idea is that so we have a spacetime, which for the cases we're interested in are spacetimes with negative curvature, sort of similar to the Lobachevsky plane or hyperbolic plane. And the idea is that we have gravity in these spacetimes, and it is described by a theory that could live on the boundary or some region very far away of this spacetime. So this is what we're calling the boundary, is really a region very, very far away. Only when we project this hyperbolic space, which is infinite, to the flat space, we see this boundary. Now, this is another way to represent the same thing. So the idea is that we can have a particle that moves in the interior of this spacetime, in this curved spacetime, and it's described by particles that are moving far away. So particles are located here far away, And this random motion of the particles tries to represent the fact that these particles are strongly interacting with each other. And then you can ask, how would we describe a black hole? So a black hole would correspond to a large number of particles at the boundary, a fluid of particles. Here I got tired drawing this set of particles, so it looks like, it doesn't quite look like a fluid, but you should imagine this is a fluid of particles. And the sorry, the temperature and entropy of the black hole is related to the temperature and entropy of these particles that are moving far away. And in cases where we can compute it, it agrees with what we expect from general relativity in the interior. So the theory on the boundary obeys the rules of quantum mechanics. And so then the black hole in the interior would also obey these laws of quantum mechanics. So black holes would be consistent with quantum mechanics if you accept the holographic conjecture. So this idea of holography is that we discussed in the beginning is really a conjecture which has some evidence, but it's a theoretical conjecture. Yeah, let me. So now we'll emphasize one aspect of holography. So this aspect of emergent geometry, and so the idea is that we have qubits that live here on the boundary, and we have the space-time in the interior. So the gravitational space-time has one more dimension, and I will explain this using an analogy. And the analogy is again, we'll go back to these phrases that we were talking about before. So imagine we have a phrase. So this is a sentence that says that if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. So this is a full sentence. And when you hear this sentence, you perhaps you can do a grammatical analysis of this sentence. And so you would start separating the sentence in each of the words. Then you would group the words into bigger structures, bigger grammatical units. You have a first clause of the sentence and a second clause of the sentence. And then you have some correlations between the words in the sentence, like these three words are correlated. Also, there is a correlation between the idea of keeping pace and drummer. That is a deeper, let's say, correlation. But what we see is that when we do the grammatical analysis, it's a bit like there is a new dimension that appears, which is the depth of the sentence, right? The depth of analysis of the sentence. So there's a shallow analysis where you just look at each word individually. And then there is a deeper analysis where you look at the various words together, and the correlation between these words gives us some idea of the meaning of the sentence. But the meaning, in some sense, is contained at this deeper level of analysis. It's not contained just within each word. So in some sense, there is a new dimension, the dimension of the depth of analysis, let's say. So in this analogy, the idea is that the sentence would be like the state of the quantum system here on the boundary. So there's a quantum state that is a very complicated state. And what the geometry does is it characterizes the correlations between the words, or the correlations present in this state, and is representing an analysis or a description of this state, of the correlations between in this state. And you could say that someone who lives inside this space-time is a bit like a character in a novel whose text is written here at the boundary, right? That's roughly an analogy. Now we can ask, what is a black hole in this space-time? So we can go back to the sentence. So this is the same sentence that we had before. And now we will change some words. So we changed some random words. And now we lost some of the correlations. For example, we changed the word drummer to lecturer. And so now we don't have the correlation that was there between keeping pace and lecturer. And so the sentence does not make as much sense as before. and we can analyze it up to a certain level of depth, but at some point it ceases to make sense. So we can say that there is a kind of horizon of meaning. So we lost the long distance correlations in the sentence, we lost the meaning of the sentence at some level. Now we can change some more words, we make more changes, and as we make more random changes, the sentence makes less sense. So this horizon of meaning grows and becomes bigger. Okay, that's related to this idea that the area grows if we make random changes. And if we change this completely, so we change all the letters, then it doesn't make any sense at all. And the idea is that now the black hole grows and the ignorance, which was related to the area, becomes bigger. And the idea that the area would grow is related to the idea that random changes will mess up a sentence and make it more complicated. And not just more complicated, we will lose the meaning. Now, suppose that these changes came from a reversible process. For example, an encryption algorithm, the kind of algorithm that one uses to communicate safely through the internet. Right? So in that case, you can reverse this and reverse this process and recover the original sentence. If you know what process produced this, then you can reverse it and recover the original sentence. Now, the idea is that the laws of physics on the boundary change the state of the boundary, and it's analogous to an encryption process. It is reversible. So the idea is that we can, in principle, undo the formation of the black hole and recover the original information if you know those laws of physics. But this theory of particles at the boundary is that knowledge of the laws of physics, and we can, in principle, reverse it. It is, in principle, reversible. So the lesson from this story is that spacetime emerges from quantum entanglement, and in other words, it emerges from correlations that are present in the boundary quantum system. We can say that in this description, the geometry is related to patterns of entanglement, of patterns of correlations. It's somewhat similar to the idea that the meaning emerges from correlations between different words. Now, here I'm just showing you the similarity between two pictures. So this was the picture that we had with the analysis of the sentence. And this picture here is a picture that represents certain mathematical descriptions that people have given for complicated quantum systems. So independent of everything that I told you about holography and gravity and so on, people have developed ways to describe correlations in quantum systems. Some mathematical technique that is called tensor networks. And so there are some formulas behind this, concrete formulas behind these pictures. And what I want to point out is the similarity between the two pictures, that we have here a quantum system that lives here in basically one dimension, and we have this picture basically in two dimensions that we use to describe its quantum state. Now that's the end of the analogy for now. We'll discuss an extreme case of the relationship between entanglement and geometry. And so there's a funny feature about the simplest black hole solution. And the funny feature is that it describes actually two black holes. And this was first noticed by Einstein and Rosen in 1935. So the idea is that the simplest black hole solution describes really two black holes that could be roughly like similar to the solution you would have for two black holes that are far away, but that they are sharing a single interior. So the geometry at a given moment in time is a bit like a wormhole, that where you can start here, you can, if you move very fast, faster than the speed of light, you can go in one and come out at the other. That's the geometry of space at an instant in time. Now the interior is time dependent. It stretches and collapses, so we cannot go from one side to the other. So at some moment in time, this is what the geometry looks like. It joins these two far away regions. So this is the geometry very near the black hole and how they connect between the two sides. Uh, but as time progresses, these two sides are getting further away and they're becoming thinner. And at some point, this will become very, very thin. And that's the formation of the singularity. And so even though the geometries in space are connected, when we consider the full space-time, they're still connected, but a physical observer that is limited by the speed of light cannot cannot enter here and go out on the other side. So you cannot use this to send signals to faraway regions. And the quantum interpretation of this classical solution is that it basically corresponds to two entangled black holes. So each black hole has some entropy and has many possible microstates and many possible states. And in this full solution, these states are correlated between the two black holes. Now let me discuss this with an analogy. Let me go back to the analogy we had before. So imagine that we have a sentence, the same sentence we had before, but now it's a sentence in English. And we have here the same sentence in another language. Let's say here I wrote the same sentence in Spanish, okay? And so you can do some analysis of these sentences. And so the words are different and so on. But at some point you have a common meaning. So the analysis is different for each of the sentences, but at some point they converge on a single meaning. And we can think of this as a kind of wormhole, if you wish. It's somewhat analogous to the wormhole we had before. Now, okay, yeah, let me discuss this. So this wormhole is not traversable. You cannot send signals. But if you bring these two black holes closer together and you allow some interaction between the two black holes, then this wormhole can become traversable. So in the sense that you can now send signals through this wormhole. But it's not a shortcut in the sense that it takes longer to go through the wormhole than outside the wormhole. And in quantum mechanics, this process is related to something called quantum teleportation. And when spacetime is emergent, this teleportation happens through this wormhole. So let me make some analogy for what this quantum teleportation is, this signal through the wormhole. Now, we need three elements. One is entanglement, which is a type of quantum correlation. Then we need some communication. And then we have some notion of this wormhole. So let me make an analogy. So imagine that Bob and Alice, so we have Bob and Alice, and they have been married for many, many years, and they share many, many common memories, okay? And then there might be a communication. Perhaps there is a look. So Alice looks at Bob in a certain way, and Bob immediately knows what Alice had in mind and knows exactly what to do. So that's so an idea went from Alice to Bob through a simple look. Okay. So so the idea is that we have let's say some emergent universe of Alice's ideas, and similarly some emergent universe of Bob's ideas, and they're correlated because they were formed through shared memories. And so a simple look that for an outside observer would be completely meaningless, for them it allows them to transfer an idea from Alice's mind to Bob's mind. Okay. And we can say that this goes through some kind of wormhole in the sense that the outside observer does not know what that idea is, but they do know. Now, I describe these particular wormholes, which are basically a curiosity and not particularly relevant for the black holes that exist in nature. However, similar but mathematically more complicated wormholes are important for understanding how information is encoded in Hawking radiation and the black hole interior. And this is something that was recently understood by a series of relatively recent papers. So in conclusions, I try to convey the idea that certain quantum systems can lead to a geometry that is similar to the geometry of general relativity, and this happens through correlations. Our space-time geometry could be emergent in that way. Perhaps that's one possibility. And this has some an interesting consequences. So we could make, in some sense, tiny universes in the laboratory. I put universes in quotes. I will explain what we mean. Um, so the idea is that in principle, we could artificially make some of these quantum systems that describe some geometry with a quantum computer, with a suitably complicated quantum computer, and build what we would call the small universe. So what we mean is that this quantum system would be complicated enough that it will have some emergent geometry that is described and governed by Einstein's equations. Okay, so it won't be exactly like our universe; would be much tinier, and the particular equations are a bit different, but they will have in common that they will be governed by Einstein's equations. To make the simplest universe of this kind, you would need about 10,000 qubits. Just for reference, the current quantum computers have a much smaller number for their, about 12 error-corrected qubits. In our contrast, our big universe would need about 10 to the 120 qubits, so much bigger. So we will not be able to make our universe. But we would, in principle, be able to see some of these ideas in the far future. Well, maybe in 30 years, people say that they might get quantum computers with this number of error-corrected qubits. Now, hopefully, this will lead to an understanding. So the main reason we are doing this research is to understand the singularity inside black holes. And after we understand the singularities of black holes, we'll hope to understand the singularity at the beginning of the universe, which is the main goal of doing this research, to understand how we can describe the beginning of the universe. But that's not something we can currently understand. Okay, thank you.
Большое спасибо. Слышно ли меня? Скажите, пожалуйста.
Да, все слышно.
Да,
Yes.
отлично. Огромное спасибо за лекцию. Я сейчас буду читать вопросы из чата и послушаем ответы. Первый вопрос от Романа Морячкова. Как вы считаете, квантуется ли гравитация и какие наблюдения, эксперименты могли бы это показать?
Sorry, could you repeat the question? Whether gravitation can be what? Could you repeat the question more slowly?
Да, вопрос такой, я так понимаю, Роман имел в виду, как вы считаете, квантуется ли гравитация? Квантуется ли она? И какие наблюдения могут показать это квантование?
Okay. Yeah. Okay, I interpret the question as asking what observations can show that gravitation is quantum, right? I think the most promising observations would be the observations of the so-called primordial gravity waves through inflation. So there's this theory of inflation, which is the idea that the early universe expanded very rapidly, a theory developed by Guth, Linde, and so on. And according to this theory, quantum effects can produce small fluctuations, and the simplest fluctuations are density fluctuations that have already been observed. But in addition, this period of inflation could produce fluctuations in the geometry of space-time. So it could twist somehow the geometry of space-time. And we would see that in our present universe as very big gravity waves, very long wavelength gravity waves which are basically the size of the universe. And the idea is that we would see these gravity waves through some imprint, some signals in the cosmic microwave background, in particular through the polarization of the cosmic microwave background. And this is something people are searching for, and maybe it might be discovered in the next few years. I think this is the most, and this would be evidence that gravity was quantized. or is quantized, but is evidence of quantum gravity effects in the early universe.
Спасибо. Кирилл, попросите, пожалуйста, Хуана включить камеру, если это возможно, потому что его не видно.
Oh, sorry. Okay.
Да, спасибо. Следующие там 3 вопроса от Татьяны, и они довольно длинные. Первый вопрос такой. В классической квантовой физике время обычно рассматривается как измерение пространства-времени. Но в моей концепции время первично, а форма и пространство возникают позже. Возможно ли рассматривать время как фундаментальное явление, из которого вытягиваются пространство и события? Есть ли в этом контексте критические точки во времени, которые могут играть особую роль, аналогичную сингулярностям в пространстве?
Yeah, so I think the idea is that in standard quantum theory, the time is an external variable. And in general relativity, we normally think about space and time together. And so, in fact, in general relativity and in quantum general relativity, the fundamental description would have no time, and you would have to find some variable which can act as time. So there has to be something changing in that space-time that can act as a time. And so the idea is that we would have some sort of description of the full thing which does not have a fundamental time, but is in some quantum state. And then we would divide that quantum state into two parts. One will be something we will call a clock, some property, some physical system that will act as a clock, and then the rest of the system. And then we can say how the rest of the system changes as that clock changes. So that's something that is necessary to discuss even in general relativity in general. I mean, in ordinary circumstances, like in our expanding universe, for example, we can think of the clock as the overall size of the universe, and in that case, there is some clock variable, or we can think of the clock as the average density of matter in the universe, and that can act also as a clock.
Спасибо. Я не уверена, что Татьяна... Я не знаю, понятен ли ответ. Давайте следующий вопрос Татьяны. Если рассматривать кротовую нору как мост между пространством и временем, можно ли говорить о том, что горизонт событий – это своего рода ячейки событий, которые фиксируют квантовую информацию о прошлом, настоящем и будущем одновременно в одном моменте? Можно ли это согласовать с идеей, что информация не теряется, а распространяется по структуре пространства-времени?
Yes, I mean, the idea is that the geometry of these wormholes are encoding correlations that exist between the information as viewed from outside the black holes. And indeed, when we think about recovering information and so on, these wormhole effects are important. So the answer is to this question is essentially yes, but I haven't described in detail how that happens. And it's not completely understood in detail, but we understand many aspects of that through recent developments.
Хорошо. И третий вопрос. Если рассматривать начало инфляции, когда неоднородности в плотности, такие как инфлантоны, закладывали реликтовое излучение, можно ли вообще представить ситуацию, что частица инфлантон или какая-то другая сверхпохожая частица в будущем при расширении Вселенной и потенциально существующей в ней ее границы материи снова вступит в столкновение с нашей Вселенной? Можно ли вообще такое описать через квантовое состояние и в масштабах подобных частиц? Кирилл, удачи в переводе.
I think I'm not sure I understood the question. So I think the question is about the future of our universe. Um, so in the past, the universe was very simple and, let's say, hotter than it is today. And then the universe is expanding. And we think that the universe will continue to expand for a very long time, many times the current age of the universe, and will become colder. And perhaps in the far future, this current universe maybe might decay into some other form where the laws of physics are different. I mean, that's roughly what we expect the future of the universe to be. So I don't know if that is what the question was about.
Хорошо, следующий вопрос. Если черные дыры бесконечны, то мы в некоторой степени находимся в черной дыре?
Well, black holes are not infinite, but I think your question still makes sense. So the when you are in an expanding universe where that is expanding, let's say first with a constant expansion rate, so that it's always let's say that the Hubble, what's called the Hubble constant, is constant, then there is a sense in which there is a horizon also for you as an observer in that universe. You can only observe a region of the universe. And for the same reason that we discussed that there would be a temperature for the universe, the Hawking temperature, then there would be also a temperature for you as an observer in that universe. Now, for us in our present state, that temperature is very, very, very small. It would be the wavelength of that thermal radiation is the size of the universe. It's very, very tiny. However, in the past, in that inflationary period that we mentioned before, the universe was expanding much more rapidly, so very, very quickly. The Hubble constant was much larger, and the effects of the temperature were also much larger. And that temperature then would give rise to, or we think it gave rise to the fluctuations, primordial fluctuations that we now see in the cosmic microwave background, density fluctuation. So in fact, some of the things that we learned about black holes can then be applied to cosmology, and we apply them in cosmology, and they form the basis of some of our current description of the universe.
Спасибо. Короткий вопрос. На какое расстояние можно приблизиться к черной дыре, не рискуя быть ею захваченным?
Well, in principle, up to the horizon. Now, if you are very close to the black hole, you would have to accelerate with very large acceleration in order not to fall into the black hole, right? And then whether you can survive that very large acceleration depends. Well, first of all, you have to have a rocket that is powerful enough to give you that large acceleration. And second, you might or might not survive it. Now, for an astrophysical black hole, which is, let's say, has a mass of the order of the solar mass, the curvature of so we'll have a radius of roughly 1 kilometer, and you might think that you could get, let's say, so if you get to within 1 kilometer or maybe 2 or 3 kilometers from such a black hole, the accelerations that are involved are so large that they will kill you. So it will kill an ordinary person. Even if you are falling freely through this black hole, just the tidal forces will kill you before you get to the horizon. So that's because we as humans are very afraid. But so if your question is about us, we cannot get very close of a real black hole. if the question is about an elementary particle or a robot and so on, then you can get closer.
Спасибо, да, там были приливные силы, которые разрывают тело, если оно приближается к черной дыре. Так, и следующий вопрос. Огромное спасибо за очень ясное изложение сложных идей. Как вы относитесь к тому, что в центрах галактик находятся не сверхмассивные черные дыры, а выходы кротовых нор?
Well, I discussed wormholes, and but there is a difference between the simplest black hole solution that I mentioned that the simplest Schwarzschild solution is a wormhole. However, the simplest Schwarzschild solution does not have matter inside and is eternal, and it would be very difficult to make. On the other hand, we have the theory of how those black holes form. We think that those black holes form from collapse of stars and matter, and those black holes are not wormholes. They have only a single exterior, and inside they have matter, so the geometry is different than in the interior, certainly different than the geometry of the Schwarzschild black hole. And so the short answer is we don't think that those are wormholes, that the black holes that are formed in our universe through ordinary astrophysical processes are not wormholes. They are black holes with only a single side.
Спасибо. Так, Галина Михайловна, ваши рассуждения позволяют приблизиться к лучшему осознанию природы физических законов на основе аналогий. Картину Эшера «Ангелы и демоны» я видела в иллюстрациях подобных объяснений. В 2000 году вышла книга Мартина Риса «Всего 6 чисел», а в 2022 году сделан ее русский перевод. 2 из этих чисел связаны в основном с силами, а другие 2 определяют размеры и общую структуру Вселенной и показывают, будет ли она существовать вечно, а еще 2 говорят о свойствах самой Вселенной. Мы могли появиться и можем существовать только при определенной правильной комбинации этих 6 чисел. Как вы считаете, в каком объеме можно и можно ли вообще знакомить школьников с подобными вопросами?
I didn't completely understand the question, so is the question about the fine-tuning of the forces?
Вопрос заключается в том, насколько имеет смысл рассказывать школьникам о существовании 6 фундаментальных констант, как я понимаю, которые определяют возможность нашего существования в Вселенной.
Okay. Yeah, so let me try to say what I understood about the question. So in nature, we have various fundamental forces. So the electric force, the weak force, the strong force, and they form the structure of the so-called standard model of particle physics, which is the particular quantum field theory that we use to describe nature. Now, this description contains constants of nature, so some numbers that we have to measure that are not cannot be predicted. They have to be measured, and these numbers are, for example, the electron charge, the mass of the electron, some constants that determine the mass of the proton, and so on. Now, these values are somewhat special in the sense that if you were to change these values a little bit, life as we know it might not be possible. So, for example, if you change the particular values of some of the quark masses, then it might be that the neutron becomes stable and the proton becomes unstable. And if that happens, then atoms would not be like they are today. So life as we know would not be possible. And now, so it is a funny feature of nature that these values seem to be special, and the question is, why do they have those special values and why not different values? Now, one possible explanation for these special values is that perhaps there are different regions of the universe, and in other regions they take different values, and the values that they take here in our region are have this special form because they make life possible. So we would not be able to live in a place where the neutron was stable and the proton was unstable because there were not the atoms and life as we know it. So that's a possible, let's say, explanation of that. It's called the multiverse explanation for those coincidences, if you wish.
Окей, спасибо. Следующий от Вероники. Огромное спасибо за невероятную лекцию. Корректно ли в современных голографических подходах понимать под тканью пространства-времени прежде всего структуру квантовой запутанности, а энтропию как ограничение на возможные степени свободы геометрии? И если так, остается ли место для каких-либо фундаментальных единиц пространства-времени, учитывая то, что мы знаем об энтропии черных дыр и излучении Хокинга? И если пространство-время эмерджентно, телепортация всегда рассматривается через черную дыру, или это был частный пример? Я так понимаю, что это два разных вопроса.
As I said, we don't have a complete theory of quantum gravity yet, so we cannot say what the complete theory is. This holographic approach seems to work well for certain spacetimes. And in those spacetimes, the idea is that all measurements you can make far away can be described in terms of this quantum field theory, which is a theory whose rules we understand. Now, entropy and quantum correlations play an important role in making space-time appear. The main reason that they play an important role is that there is this simplicity of Hawking's formula that says that the entropy is the area. So that formula relates entropy to geometry, right? So, and that's why we think that in general geometry comes from correlations. It's based essentially on that formula. To be more precise, there is a generalization of that formula that is what is really relevant.
Да, там еще была вторая часть вопроса. Телепортация всегда осуществляется через черную дыру, или это был частный пример?
Good. Yes. Well, the short answer is no. So when people discuss teleportation, they discuss teleportation for using a small number of qubits. So the simplest case is when you have two entangled qubits. So where Alice has one qubit and Bob has the other qubit, and they're entangled. And you can teleport the third qubit using the standard teleportation protocol. And so teleportation happens through wormholes in the special cases where you have complex quantum systems that have a gravity description. So I mentioned in the beginning that in order to have some spacetime that is described by Einstein's theory, you need the particles to interact very strongly. And so there are very special systems that have this gravity description. Now, it could be that even so that's what we understand today. Maybe I'll leave it there. So let me summarize that. So the cases where you can think of teleportation as happening through a wormhole are very, very special cases.
Спасибо. Следующий вопрос от Михаила. Касательно последних слайдов про тесты на квантовых компьютерах. Обычно для голографии предполагается антидеситер топология. А как насчет реализации этого в лаборатории? Предположительно, там это не реализовать? Насколько экспериментальный тест будет полноценной аналогией в таком случае?
Yeah, so the idea is to simulate. So I mentioned that gravity can be described by a system of interacting particles on the boundary, right? So the idea is to make a quantum simulation of those interacting particles on the boundary. Right? So in principle, a quantum computer can simulate any quantum system. So if you have a sufficiently complicated quantum computer, you can simulate any quantum system. And so that tells you that in principle you can do it. And what I showed was an estimate of the number of qubits that you would need to actually do that.
Окей. И последний вроде бы вопрос из чата. Излучение черных дыр – это перспективно? Может заменить время на периоды эволюции Вселенной? Я не очень понимаю этот вопрос, но попробуйте задать.
Could you repeat the question?
Ну, написано вот так. Изучение черных дыр – это перспективно? Да, там, изучение, извините.
Good. I think the question is, how do we study black holes? Well, there are astrophysical black holes. By that, what I mean are the black holes that are produced in our universe through the collapse of stars and so on. And these are very big black holes of sizes of kilometers up to billion of kilometers. And these are all studied using astrophysical observations. Now, for those black holes are very well described by the classical Einstein theory. So the things I discussed today are not relevant for those black holes. And right now we are living in a golden age of black hole observations. There are many ways in which people are studying those black holes. They study them by looking at the gas that is around the black hole, and we saw some pictures of that during the talk. And we also study them by looking at black hole collisions and the gravity waves that are emitted by these black hole collisions. Now, for the things that I discussed in this talk, the best way to study them, I think, will be through these quantum simulations. And that cannot be done now, but will be done in the future.
Так, спасибо. И еще тут один вопрос появился. Не окажется ли прилив той силой, которая покажет неполноту теории относительности? Ведь разное притяжение в разных точках делает принцип инерциальности систем локальным.
I didn't understand the question.
Сейчас вопрос про приливные силы. Значит, Леонид Зотов хочет понять, не противоречат ли приливные силы теории относительности. Ну, точнее, не показывают ли они неполноту теории относительности.
Oh, yeah. Yes. No, there is no contradiction. So the tidal forces are an essential part of the theory of relativity. So when we discussed this experiment of the elevator, this Einstein's happy thought, we said that the main effect of gravity disappears, so that the weight, when you are falling freely, the main effect of gravity disappears, which is your weight. But there is an effect of gravity that remains, which is the tidal force. And the tidal force is proportional to the curvature of the geometry. It's directly related to the curvature of the geometry. Now, the tidal force means that if you're falling through a gravitational field, your head might be pulled in one direction and your feet might be pulled in the opposite direction, for example. Yeah, so that, of course, this is the same effect that gives rise to the tides, the ocean tides on the Earth. Right? That's why they're called tidal forces.
Так, есть ли у нас еще время на вопрос?
Можно
Там
еще
есть...
задать. Да.
Да, еще вопрос от Александра, но я не знаю, как его прочитать, чтобы перевести. Сейчас. Илон Маск предложил использовать энергию Солнца. Вы согласны с этим? Период Вайвер исключение. Я не знаю, я не понимаю, что здесь написано.
About the use of which energy?
Да, ну сейчас здесь написано так. Период Вайвер, исключение из правил. По-моему, мы сейчас живем в этом периоде. Илон Маск предложил брать только энергию Солнца. Согласны ли вы с этим? Я не очень понимаю, о чем речь.
Well, I didn't understand what Musk said. So I guess we have the energy from the sun that we can use, and that's perfectly good to use the energy from the sun. Of course, it's renewable and so on. The question is whether we should use the energy from oil or fossil fuels and so on. Well, I guess that energy will run out and it's causing problems for global warming and so on. So it's problematic. But I guess we'll end up switching to solar energy in probably not so far future. Actually, the prices of solar panels are becoming lower and lower. So at least in places where there is a lot of sun, we'll continue to use, but we'll start using more solar energy.
Спасибо. И давайте самый последний вопрос, пока больше не вижу. Вот есть еще один. Благодарю за вашу лекцию. Вы показали, что кротовые норы могут быть связаны с квантовой запутанностью, а черные дыры с информацией на их границе. Означает ли это, что пространство и время на самом деле не являются чем-то первичным, а возникают из чего-то более глубокого, например, из квантовой информации? И если это так, как тогда мы должны понимать такие понятия, как здесь, там, раньше, позже в квантовой теории гравитации?
Yes, in this description, it looks like space-time is a derived concept, an emergent concept, which is not fundamental. There might be another description where it's fundamental that we don't know. Now, how do we describe here and there and so on? Well, I would say that remember when we were doing these analogies with sentences and so on. So we are like characters in a novel. So here and there are, they are described by the text in the novel, where the text of the novel describes where we are.
Хорошо, спасибо. Ну, тут еще один вопрос появился.
Давай.
Коллеги, давайте самый последний. Да.
Последний.
Существует ли, на ваш взгляд, объективное время без наблюдателя? Или время возникает только как описание этих самых корреляций между квантовыми состояниями?
Well, it depends on what you call an observer. So I think the time is related to correlations in the quantum state and correlations between a clock or the observer and the rest of the system. So whether that observer needs to be conscious and a person like us, that I don't think is the case. I mean, time existed before there were people and so on. But there should be a physical system that can act as a clock and then the rest of the universe, and we have correlations between these two things. So that aspect is important. So the observer doesn't have to be as sophisticated as us, but always we will have a correlation between two physical systems in a state that contains no time. That's part of the standard general relativity discussion.
Спасибо. Наверное, на этом мы... Большое спасибо Хуану за лекцию и за все эти ответы на большие длинные вопросы, сложные. Спасибо всем слушателям, кто задал вопросы.